OK, the last mitigation we will talk about is something called address space layout randomization, or ASLR. So going back to our favorite picture, where we talk about the steps of an attack, we have learned how to make it harder to execute shellcode by adding non-executable pages. We have learned how to make it harder to overwrite the RIP by adding stack canaries and pointer authentication so that attackers that write from bottom addresses higher up will clobber out those secret values. And now, in the final mitigation we'll see, we're going to target step 2, where the attacker writes the shellcode somewhere that they know so that they can use that same address to overwrite the RIP. So this is the last defense that we're going to see. It's called ASLR. So to motivate ASLR, let's take a look at this picture. We've seen this a lot. This shows us the 4 sections of memory. But in real life, when you are running programs, you are probably not using all of this space for the code. And your stack is probably not using all of this space either. So in real life, your programs don't really look like this. They look like this. You have a stack and a heap and the data section and the code section, but you don't really use most of memory. Your programs are not running using 4 gigabytes of working memory most of the time on a 32-bit system, or what was it, 18 billion gigabytes in a 64-bit system. So most of the address space is just totally blank. Your program's not using any of this stuff. So this gives us an idea. If the program's not using any of this stuff, what is stopping us from taking stack, heap, data, code, and changing where they appear on the stack? Sometimes when you run the program, they can live here. The next time you run the program, maybe you shift them up a little bit, so all the addresses move up a little bit. And to get even more creative, what's stopping you from shuffling them around? Why not put the heap up here, and the stack down here, and the code over here? That's going to work too. The stack can still grow down if it needs more addresses. It's not going to need all of this space. The heap can still grow up. That's not a problem. So what we're getting at here is if each of these segments of memory only uses a tiny amount of the address space, well, then nothing is really stopping you from shuffling them around each time the program is run. So when you run the program once, you get this layout. The next time you run it, you get this layout. The program runs just fine. But what you've done is you've changed the addresses. You've made it harder for the attacker to guess where things are on the stack. So that's what ASLR does. It takes advantage of the fact that there's all this unused space, and it shuffles around where the memory segments are placed every time you run the program. So that's called ASLR, and this stops the attacker from doing their classic buffer overflow exploit. Because what do you do in the classic buffer overflow exploit, the very first one we saw? You write shellcode, and then you overwrite the RIP with the address of shellcode. But if the address of shellcode moves around every time you run the program, what address do you put in the RIP? Who knows? Now you've made the attacker's life harder. They don't know what address to put in the RIP. So now the attacker's life is harder. They can no longer do the classic buffer overflow exploit because addresses shift around every single time. And ASLR can shuffle all 4 segments of memory as we saw. So you can shuffle them anywhere you want. And now wherever you put shellcode, you don't know what the addresses are. They're different every single time. And something to mention, by the way, when we're talking about ASLR, is that when it shuffles the segments of memory, it doesn't shuffle what's inside that segment. So what that means is that relative addresses are still the same. So we could take the stack and drag the entire stack upwards so that instead of addresses 1,000 to 2,000, it now lives in addresses 4,000 to 5,000 or 8,000 to 9,000. That's something you can do. But within the stack, you can't shuffle things inside the stack. That would break the program. So you can't go in the stack and just shuffle everything around. Now no one knows where anything is. Inside the stack, everything is still in the same relative location. So for example, when you build a stack frame, it's still RIP first, followed by SFP, followed by local variables. That does not change. The local variables are below the SFP, which is below the RIP. The relative ordering is the same. It's just they have shifted from being 1,000 to 2,000 to 8,000 to 9,000, or something like that. So while it shuffles the segment, it does not shuffle what's inside the segment. As always, we will ask how this does performance-wise. ASLR's performance overhead is pretty low. So the reason why is because your operating system is actually already doing this without really telling you. So if you know anything about virtual memory from CS61C, you'll know that your program is already rearranging the data into so-called pages in physical memory. So you don't have to know that for this class. Just know that the operating system is already doing this for you. It's already putting code in different parts of your actual physical memory to cause the program to run. So basically, turning this on doesn't make things any slower. You're not going to notice any sort of performance benefit, so you might as well turn this thing on.